Okay, so welcome to Math 150 multivariable calculus. This is lecture 28. We are now in the home stretch. So we are now moving to the final topic of the semester, which is multivariable integration. So how many of you remember your Calc 2? All the different techniques of integration. What is your least favorite technique of integration? If you don't get this right, it's only because it was so traumatic you've forgotten you did this. Least favorite technique. No, there's something worse than trig. No, divine inspiration is great. It's just not trustworthy. Divine inspiration is you just write down the answer. You don't have to, you just have to take the derivative. Because as long as you can take the derivative of any simple function. Differentiation is so much easier than integration because you can always just take the derivative. So if you're divinely inspired, you just write down the answer and you're right. The problem is, to find the integral, how do you find it? Partial fractions. I think most people normally say that partial fractions was their least favorite integration technique. But we have lots of techniques. We have U substitution, we have integration by parts, we have trigonometric substitution, we have partial fractions. We have so many different ways of doing things. In multivariable calculus, we really only have two integration techniques. One of them is very similar to what we saw in differentiation, that if your function is nice, you can differentiate first with respect to x and then with respect to y, or first with respect to y and then with respect to x. It doesn't matter which order you differentiate. For a lot of things in multivariable calculus, when you're integrating, you can integrate first with respect to x and then y, or y and then x, and you'll get the same answer. So we'll have to talk about how do you integrate over general regions. What do you think the nicest region is going to be? The nicest shape to integrate will be? What's a good shape? Square. Square or rectangles are much better than circles. And if you think about polar coordinates and spherical coordinates or cylindrical coordinates, we haven't done too much with them so far this semester. What they basically do is they convert regions that are not rectangles to rectangles. A circle in polar coordinates is a rectangle. A sphere in a sphere in spherical coordinates is a box. And so we convert the region of integration to being something nice. You can't always do this with a change of variables, so we're going to have to talk about how do you integrate over general shapes. There are only two real techniques in multivariable calculus for integrals. One of them is switching the order of integration. If you have a double integral, how many ways can you order the integrals? Two. If I give you a triple integral over x over y over z, how many ways can you order it? Six. If I give you a quadruple, 24, 4 factorial, right? So you have 4 choices of which one you do first, 3 second, and so on and so on. So the more integrals you have, the harder it's going to be in terms of the number of possibilities, but it's still finite. In this class, we're really only doing 2 or 3 dimensional integrals, so there's not going to be that many possibilities. So if you're doing an integral and it's not working well, one possibility is switch the order of integrations. And if it's a double integral, there's only really 2 things to try. And if you switch and it's not working, switch back, and maybe the other one wasn't so bad after all. The other thing we have is change of variables. And change of variables, there's a couple of standard ones. The big 3 are polar, cylindrical, spherical. I can't disguise when to use them, right? If you're integrating over a sphere, which coordinates do you think you should use? Spherical. And then you convert the region, instead of integrating over a sphere, to integrating over a box. But we have to then figure out, what does dx, dy, dz, the little volume element, become in spherical coordinates? And that's going to be a big part later on. So before we do all this, we need to generalize a little bit the fundamental theme of calculus. So one part of the fundamental theme of calculus is that we have these Riemann sums, and in the limit they converge to the area, and this is the antiderivative at b minus the antiderivative at a. We're not going to be able to get a formula as nice as that in several variables, because in general it's hard to get antiderivatives, and we have a little bit more bigger region. So what we're going to talk about instead is, what do we mean by integrating in several variables? We'll talk a little bit about the process, how it's going to converge, and then we'll talk about some of the properties of integration. Okay? And then in the next class, we'll continue and we'll start talking about switching orders of integration and how do you integrate over different regions. Or maybe we'll do that on Friday, and maybe we'll do an application on Wednesday. I want to give you a sense of why we actually care about all this stuff. The other thing, of course, is that most integrals can't be done in closed form. And so even with switching orders of integration, even with converting things to, maybe spherical coordinates or whatnot, we're going to be left with integrals we can't evaluate. So we're going to have to talk about how would you numerically approximate an integral. If you want to go into finance or economics, you often have 300-dimensional integrals that you need to evaluate. You're not going to be able to do this in closed form. So what you need to do is you need to find a way to numerically approximate these very well, very quickly. And so we'll talk about that because I want to keep giving applications of what we're doing. Why are we spending time learning this? Okay, so the first thing that we should really talk about is the basics of integration. So basics of integrals in several variables. So let's think about what's going on. So let's do things in 2 dimensions. So I have very little artistic skill, but let's say I have something like this, where I have some kind of region like this, and here is my xy plane, and then maybe I have some function over the xy plane. And I want to find, in 1 dimension, I did the area under the curve. Here, I'm going to find the volume under the surface. So let's find the volume under the surface. So we start with a rectangle in the xy plane. Maybe A less than equal to X less than equal to B, C less than equal to Y less than equal to D, all are finite. And so we're going to just do finite integrals, finite regions. As soon as you have an infinity, this is a danger sign. You've got to be careful every time an infinity emerges, okay? As long as we keep things finite, it's much easier to show that things will converge. If you want to do something that's infinite, what you often do is you do a limit as maybe B goes to infinity. And slowly you do some kind of rigorous arguments like that. In your Calc 1, Calc 2 class, probably more Calc 2, they might have talked about indefinite integrals. They might have talked about improper integrals going off to infinity, stuff like that. How do we handle something like that? You need to have some kind of decay in your function for things to converge and for things to make sense. All right, so we're going to chop things up in each rectangle. What we can do is we can do Riemann sums. So look at max and min in each rectangle. Sum, take limit, show converge to a common value. And we denote this by the integral over R of f of x, y, dA. And here, R is going to be the rectangle AB cross CD, which means all points x, y, x is in AB, y is in CD. This is extremely similar to what we did for Riemann sums. For Riemann sums, what did we do in 1 dimension? We chopped up the x-axis. For each subinterval, we looked at where's the function largest, where's the function smallest. We got our upper sum, we got our lower sum. We showed the upper and the lower sums converge to a common value. That common value we call the integral. And then we showed the fundamental theorem of calculus that that integral is the antiderivative at B minus the antiderivative at A. I did it again. What word did I use wrong? V, very good, right? What word should I have used? A, it's an antiderivative at B minus that same antiderivative at A. We do the same thing in several variables. rather than chopping up the x-axis, we chop up the rectangle. And then we just show for each little box, for each little smaller rectangle, we find where's the function largest, where's the function smallest, and we show that this converges. If you, question?
What are the intervals? Is that dA?
dA, right, for area. And what letter do you think we would do in 3 dimensions? V for volume. So again, always think about what letters you're using so that things are nice. So right now I've introduced a definition. The way we find the volume under the surface is we chop up the rectangle into smaller bits, we calculate the upper sums, we calculate the lower sums, and they converge to a common value, and that value is going to be the volume. Yes?
So are we taking like the small bits as in those each little squares and adding them all up?
Yes, so for each little square, we find where is the function largest, where is the function smallest, and we form the upper sum and the lower sum. And then what you would do is you would just keep dividing. So, for the next level, maybe we would, divide, again, and you keep dividing. And as you divide more and more and more times, it should become more and more accurate, and it should converge to what the true volume is. So right now, this is a way to compute the volume. If anybody is excited about computing volumes like this, you have an issue. If you have a question, please ask. Because what's the, you figured it out? Okay. So no one should be excited about calculating volumes like this. To do a volume like this, you have to do a limiting process. What's so wonderful about the fundamental theorem of calculus is that it reduces a lot of these calculations to just finding antiderivatives. Wouldn't it be nice if we could do the same thing here? So what we would love to do is to somehow convert this to integrating over x and then integrating over y. Okay, so now, if you could control the universe and you could set the rules for differentiation, what would you choose the derivative of a quotient to be? Or the derivative of a product? If you could choose the product rule, what would you have chosen the product rule to be?
No product rule, and just multiplying and then.
Yeah, the derivative of a product would be the product of the derivatives. What would you have chosen the quotient rule to be?
The same.
Yeah, the same. The derivative of a quotient is the quotient of the derivatives, right? Sadly, you don't have that power. I don't have that power. That's not what the product rule is. But we can hope. We can always hope. And sometimes the hopes are not dashed. What could we hope for the integral? We could hope that the integral over r of f of x, y, dA is equal to the integral x goes from a to b, integral y goes from c to d, f of x, y, dy, dx equals integral y goes from c to d, integral x goes from a to b, f of x, y, dx, dy. That's a really good hope that the way we calculate a double integral like this over a rectangle is first fix a value of x and then have y go from c to d, calculate what's going on, and then sum that up over all the x's. Or conversely, fix a value of y, see what's going on for x, and then sum all of those up. And so just trying to look at what's going on, if we look at, here's the x-axis, here's the y-axis, and let's chop things up into lots of different boxes. So here is the point, A, C, here's the point BC, here's the point BD, here's the point AD. And for each box, we look at the value of the function above it and we try to calculate what's going on. If we chop things up into lots and lots of pieces, what do you think the thickness is going to be vertically? what would you say that thickness would be if we have many, many, many boxes? You know, I can't draw, you know, a billion boxes. I'm sorry? Approaching zero. How should we denote something approaching zero? Infinitely small. What variable should I be using? Is this an infinitely small x or an infinitely small y? Y. So this might be, let's call this maybe delta y, which would be, you know, d minus c over n. And over here, this might be, you know, delta x, which would equal, you know, b minus a, and I'll do over the same n. I'll chop it up the same way for each. And then the hope is that if I fix a value of x, so I fix a value of x, and then okay, so if I fix the value of x, what I can do is I can look up like this. And I can find essentially the volume in that small little rectangular sliver. Okay, and that would be over here, it would be the integral, whoops. It would be the integral y goes from c to d of f. What's the value? X is going to be fixed at x, and y is going to be varying dy, and I would multiply that by delta x. And that would be the volume of the red, the volume under the, does everybody see that? And this is basically just what we did in one-dimensional calculus. The only difference now is rather than just going up a straight line, we have such a small change in x that really, when I write f of x, y, really this lives between x and x plus delta x. You know, if I really want to find out what's going on in this whole thing, if I truly wanted to, it's changing ever so slightly. Let's just use the value at the left endpoint. Yes.
Wait, so we're evaluating the function, but
I'm finding the area under the surface.
And then you're
Y is going from C to D. So I'm finding what is the volume under the surface in this very thin rectangle.
What about this change in x that you're multiplying? Is that
That's the width of the rectangle. The rectangle's width is delta x. The height is d minus c. So if the function was constant, it would just be the base times the height. But the function is not constant, so I keep multiplying by what the value of the function is. But the function changes a little bit as I move x. But as I move from x to x plus delta x, since my function is continuous, it changes by such a small amount, you can make this rigorous that it's really going to be a very small term. That there's going to be an extra delta x, you know, from how small that move is. It's already small. It's going to become tremendously small if I look at how much it varies. So what we're really doing is we're using almost like the mean value theorem. And so by, you know, the mean value theorem, f of x plus delta x, should be y, is equal to f of xy plus df dx at xy times delta x. So the amount that the function changes by is so small when I move it over that if I put in that correction, it's going to be a negligible change. And so I can just, in the limit, as I keep taking these small and small and smaller, I can just use f of xy. And that would give me the volume of this rectangle. And now what I do is then I let x vary. And so I would then integrate x goes from a to b. And so this dx is going to become, this delta x is going to become a dx. You know, what I'm really doing is I'm really summing over all of those boxes. So if you really want to do it rigorously at this point, you know, not doing an integral, I would then do, you know, a sum, you know, maybe I goes from 0 to n minus 1 and this would really be x sub I. And that's going to converge, and that's going to become the first piece. And then as you take the limit, as n goes to infinity. All right. I'm just trying to give enough justification for why the double integral can be written like this. If I were to do it the other way, if I were to first fix a value of y, oops, actually, sorry, I want to lower over here. I fix a value of y. Now I would have my box like this. And so I would have, the integral x goes from a to b, f of x, y, dx times delta y. And then I would do the exact same game, is then I would have a sum. So I'll make this, I'm sorry. So I would make this, a y sub I, and I would have I goes from 0 to n minus 1, and then take the limit as n goes to infinity. So this is how I would calculate areas, so how I would calculate volumes under surfaces. It's a two-dimensional integral. For each little box, I'm essentially looking at what is the upper and lower sum contribution, and I'm taking the limit. And because everything is a nice rectangle, this is going to just reduce to what we did in Calc 2, but we now do it twice. If I had a three-dimensional surface, and for each point x, y, z, I give a value, and I want to find what is the hypervolume, I would have a three-dimensional integral. And as long as things are rectangles, this is not going to be bad. The difficulty comes as soon as we no longer have a rectangle. As soon as we no longer have a rectangle, all bets are off. But this is what would go on if we have a rectangle. You can make all of this extremely rigorous. And so, again, in a first course where most of you are not going to be math majors, it's always a challenge how much detail to get into. I want to get into enough so that you can see what's going on, enough so that you can see if I wanted to make it rigorous, what would I do? If you want to see it rigorous, I'm happy to either meet with you or do an extra lecture on this. My feeling is this is enough because we did it rigorously for what's going on to just give you a sense, and now we can just use it. So the next thing is we want to have a bunch of rules of integration. So essentially, all of the rules you know from Calc 2 extend. So if I have, I'm going to just write it, integral like this over some region R of C f of x1 through xn dx1 dxn, what do you think that should equal? So if I multiply the function by c, what should that do to the integral? Yeah, you just move c out. And this is where it's nice to be, the professor. I can highlight this. Oh. Copy. Right. And so this is the same as we just moved the c outside. So that's our first rule. The second rule is, what if I had the integral of f of x1 through xn plus g of x1 through xn dx1 through dxn. So what if I had the integral of a sum or the integral of a difference? That would be the same thing. Yeah, you just split the integral to each. So this would just be, the integral over the region of f of x1 through xn dx1 dxn plus the integral over the region of g x1 xn dx1 dxn. This is exactly like what you've seen before. How would we prove this rigorously? Well, we would just interpret what's going on. If I'm multiplying the function by c, all I'm doing is I'm changing the height of my function by multiplicative constant of c. So when I'm calculating the upper and the lower sums, I've just increased every upper sum by a factor of c. I've increased every lower sum by a factor of c. So the answer is just going to be c times what it was before. If I have f plus g, then the height is just f and g. So I can just view the volume as the first surface and then put the second surface on top of it and move it up. So there's nice intuitions for all of these. So if you look at the homework problems, it asks you to find the integrals of a couple of standard functions. Oops, there should probably be parentheses around this just to make it clear. And so we just want to figure out what is the integral, and all of these are over rectangular regions. So in all of these problems, because the values are always finite and the regions are always finite, you can choose which way to integrate. So when you have the integral of x cubed dA, you could integrate with respect to x first or with respect to y first, it doesn't matter. For the second one, where you have the integral of dx dy, what this means is we first integrate with respect to x and then with respect to y. For the next one, we first integrate with respect to y and then with respect to x. And then for the last one, you can choose which way you want to do it. For some of the others, you can also choose which way you do it. You can either integrate with respect to x first or with respect to y first. And again, if it's not going well, what should you do? Try the other way. And if they're both not doing well, go back to the first one. Maybe it wasn't so bad. But as long as it's just a double integral, there's not that many choices. Yes?
So you just take the integral of the function with respect to x and just whatever that is, back to respect to y.
Well, you're supposed to integrate over the region r is -4 to 4, and y is going from 0 to 5. So if we wanted to expand and write this out, do you want to integrate with respect to x first? Then x would go from -4 to 4, and y would go from 0 to 5. And you would have x cubed dx dy, or this also equals, if we do y first, y goes from 0 to 5, x cubed dy, and then we do the x integral, x goes from -4 to 4. So you can do it either way. For some problems, one way is going to be easier than the other. So if you're doing one of these problems on the homework or the exam and it's just not working, try the other way. That's one of two main techniques we have in multivariable calculus, is switching the order of integration. Now, you cannot always switch the order of integration. That's what makes the subject so difficult. But if everything is nice, you can. If you become a pure mathematician, you can spend years trying to figure out what is the weakest definition of nice function you can have. What's the most expansive definition you can have where you can do what you want to do. And there are some people who really enjoy doing this. They want to know, what is the most basic minimal condition I need? Other people are like, I'm going to be an engineer, I'm going to build things, I'm going to be looking at functions that are really, really good. And I don't really care about what is the most general weakest condition possible. My functions are always going to be way below, the minimum level of niceness. And so I would much rather have an easier condition that excludes certain functions, but that's fine. And so when we proved the fundamental theorem of calculus, we assumed that our function was continuous, that our function was differentiable, and that the derivative was bounded. And we needed this to show that the upper sum and the lower sum converged to the common value, which was the area. What theorem did we use to show the upper and the lower sum converged? Yeah, the mean value theorem, right? Whenever I'm talking about the lecture of the fundamental theorem of calculus, it's the one with the mean value theorem. So we use the mean value theorem to show that the upper and the lower sums converged by showing that when you were really close to each other, the difference had to be small, and we use the mean value theorem. Well, if we're using the mean value theorem, we need to know something about the derivative of f. The fundamental theorem of calculus does not require f to be differentiable, but the proof is a lot easier because I can then use the mean value theorem. So if you don't want to use the mean value theorem, if you want to use more powerful results from analysis, that's absolutely fine. But then you have to do a little bit more work. You have to develop more theory. Well, it's a one-time cost. Once you have it, you now have the fundamental theorem of calculus for a larger class of functions. And you can now integrate some functions that are not necessarily differentiable everywhere. So it's worth being able to do that. But in practice, all the functions we look at are differentiable. So why not prove it in the special case when the functions are differentiable and things are nice? So what I want to do now is I want to give a warning as to how bad things can get. Giving you an example of a double integral where order matters. I'm going to give you an example of a double sum. And you can always smear this sum into an integral. It's just a little bit easier to write it down as a sum. So why order can matter. And so what we're going to do is I'm going to draw the beginning of an infinite by infinite grid. In the interests of time, I will only draw a subset of it. That should be enough. So I'm drawing the beginning of my grid. So here's the point 0, 0. Here's the point 1, 0, 2, 0, and so on. Here's the point 0, 1, 1, 1, 2, 1. Here's the point 0, 2, 1, 2, 2, 2, and so on. And I'm going to define my terms AMN as follows: +1, -1, and then 0 for the rest of eternity. Okay? I'm going to define it to be 0, +1, -1, and then 0 for all eternity. 0, 0, +1, -1, and then 0 for all eternity. 0, 0, 0, +1, -1, 0 for all eternity, and so on. Okay, does everybody understand how I'm defining my sequence? So I want to study the sum, m goes from 0 to infinity, the sum n goes from 0 to infinity of AMN versus the sum n goes from 0 to infinity, the sum m goes from 0 to infinity of AMN. So for AMN, M is the row, N is the column. So what can you tell me if we're looking at AMN where we sum over N? Have we fixed the row or have we fixed the column? So when we're doing the sum, m goes from 0 to infinity, and then the sum n goes from 0 to infinity of AMN, we're doing the n sum first. Have we fixed the row or have we fixed the column? We fixed the row. So here, the row is fixed. Here, the column is fixed. So if we fix a column, what can you tell me about the sum of each column? Each column sums to 0. So this is equal to the sum, n goes from 0 to infinity of 0. And what does that equal? 0, right? If I add 0 infinitely many times, I get 0. Now let's look at the other one, where now we fix the row. What's the sum of the first row? What's the sum of the second row? What's the sum of the third row? What's the sum of every row other than the first? is equal to the sum, m goes from 0 to infinity, and then we have 1 if m equals 0 and 0 otherwise. So this is equal to 1, and 1 is not 0. So here's an example of a double sum where the order matters. What you could do is, if you want to have a continuous function, I'll explain in a moment how you can do this. The issue is that, oops, the sum over m, the sum over n of the absolute value of a m n equals infinity. That's what actually is causing the problem. There's actually two infinities going on in this problem. One is that the region is infinite, and the other is that the sum of the absolute values is infinite. That causes problems. You might have seen a little bit of this in a Calc 2 class when they're talking about integrals to infinity. If the integral of the absolute value diverges, then we have some issues with what the integral is. I don't want to go into too much detail about this. What you could do is, if you don't like the fact that this is not a continuous function, that it's sums, is what I could do is I could take a circle about each of these points and draw a cone of volume 1, and I could smear it out. And then for over these points, I could draw a circle going below a volume -1. And so I could, and actually I guess they should actually maybe touch. So maybe I'll have the radius like a half, so that these would perfectly touch, but one would be going down and one is coming up. And so if I smear it out like that, I can make everything continuous. And now I have a double integral. And so for a lot of things, it's just easier sometimes to look at discrete examples and then pass to a continuous one. But this shows you that you have to be careful in the subject. And again, this is just the first course in the subject. We don't need to go into every detail. We don't need to prove everything. But I want you to be at least aware of the challenges and why the subject is difficult and why people have to spend a lot of time thinking about it. Bad stuff can happen. And whenever you see an infinity in mathematics, this is a warning sign. And the danger is, whenever I have an infinity, I have to think about what is the best way to handle things. So this is to show you that you have to be careful, right? And so the result, the big theorem, is the Fubini theorem. And Fubini says the following. So assume f is a continuous function on a finite rectangle AB cross CD, and we'll define that to be R. Then the integral over R of FDA is equal to the integral x goes from A to B, y goes from C to D, f of x, y. Do I write dy or do I write dx? Which comes first? Dy, I'm integrating first with respect to y, and then with respect to x. And that's equal to the integral y goes from C to D, x goes from A to B, f of x, y, dx, dy. To some extent, I am writing a little bit more than I need to. Because I'm writing, in the middle integral, f of x, y, dy, I know the integral that corresponds to it. What's the variable that corresponds to it? If I'm writing dy, is it y or is it x? It's y. Do I need to write y equals c to d, or can I just write c to d? I can just write c to d. But when there's so many variables going around, it's nice to just be explicit and write down in your integration, what is the variable? How many of you did this in Calc 2 when you did integrals? You would write x goes from A to B or something like that. Sometimes people do that even in one dimension, just to be really clear what the variable is and what's going on. I don't need to write y and I don't need to write x. It just makes it a little bit easier. So Fubini's theorem is a beautiful way to compute things. And the key condition is we need our function to be continuous on a finite rectangle. This is not the most general condition that's going on. More generally, we're okay if the integral over of the absolute value of f dA is finite. So if the volume under the surface f is of the surface, I'm sorry, absolute value of f is finite, then everything is okay. And so it all comes down to the dangers with infinity. So let's do a fun example. Let's look at the harmonic series. So we have 1 plus a half plus a third plus a fourth plus ... What does that sum equal? Diverges. So this diverges to infinity. We have the alternating harmonic. 1 minus a half plus a third minus a fourth plus ... converges to, I believe it's the natural log of 2. Yes, natural log of 2, yes. Somebody give me a number that they really like. 7, I need another number. 49, okay. Was your 49 related to the 7?
I just really like this.
Okay. So to just show you how strange things are, let's reorder the alternating harmonic. So we have the positive terms, 1. What's the next positive term? 1/3, 1/5, 1/7, 1/9. And then we have the negative terms, negative a half, negative a fourth, negative a sixth, negative an eighth, negative a tenth, ... Okay. And I was told that we like the numbers 7 and 49. Okay. What I'm going to do is I'm going to keep adding positive terms until we just pass 49. And I'm going to keep adding them in order. So this would be, 1 plus 1/3 plus 1/5 plus ... up to 1/n sub 1. I don't know what that number is. Okay. Then what I'm going to do is I'm going to add the negative terms until I dip just below 7. So minus a half, minus a fourth, minus a sixth, minus an eighth, minus a tenth, minus ... minus 1/n2. Now, what do you think I'm going to do? What do you think I'm going to do? Yeah, so now I'm going to, so I first went to 49, then I went back to 7 and I overshot 7. Now I'm going to go back to 49. And so I'm going to add positive terms now, and it'll be 1/n1 plus 2, 1/n1 plus 4. Sorry, these should be pluses. Plus 1/, say, n3. And then we'll subtract terms until we get back to just below 7, and we'll keep hopping like this. Okay. So what I'm going to do is I'm going to keep adding positive numbers until I get to 49, to 7 squared. What is the sum of all the positive numbers that we have here? What's the sum of all the positive numbers? You know the whole harmonic series diverges. What's true about the sum of the positives? It's infinity. What about the sum of the negatives? Negative infinity. So there's always going to be enough for me to add enough positive terms to get back to 49. And then I add the negative terms until I just get below 7. And now I'm going to add positive terms and I'm going to get past 49. But I know each time I do this, the maximum distance I get past 49 can't be as large as my previous time, because I'm now later in the series. I then add negative terms until I dip below 7. So I can reorder the alternating harmonic series, which converges in such a way that I can have it alternating between 7 and 49. This is to just really drive home the point that when you have infinities in mathematics, you have to be careful. The harmonic series diverges. The alternating harmonic series converges. If I give you some money, where some of it is maybe your assets, some of it is your debits, does it matter for your net worth how you add things? If you add your assets first and then you subtract your debits, will you have a different amount of net worth? No, it doesn't matter how you add your assets together. You have the same value. For this alternating series, depending on how I add the terms, I can make it whatever I want. Do I have to do 7 and 49? I could actually choose the same number. I could choose, anybody have a number they like between 7 and 49?
42.
42. Is that from Hitchhikers? No, okay. So I could choose 42, and I could keep adding positive terms until I first go past 42, and the negative terms until I first get below 42, and then positive terms until I get past 42 again. I can reorder this alternating harmonic sum so that it converges to, so that the sum converges to 42. I can make the sum converge to anything. I can make it alternate between any two numbers. This just shows you how dangerous things are. We're not going to spend too much time in the first course on this. The next couple of lectures is going to be applications. It's going to be applying to this. But I want you to be aware of just how careful you have to be. That as soon as you have infinities, you have to be careful. So whenever you are doing something on a homework, on an exam, when you are using a theorem, you have to say, what theorem are you using and why is it valid? Why are you able to use it? Okay? And so in all the stuff that we're doing here, what's really allowing us to do so many of these calculations is that we have finite objects. And so I'm just going to set things up for the next class. What we want to discuss is what's called simple regions. And this will either be Wednesday or Friday. So your X simple if for each X you enter once and leave once. Y simple if for each Y you enter once, leave once. And then simple if X simple and Y simple. So for example, let's say I give you a region like this. For each value of X, I come in, I enter, I'm now in the region, and then I leave and I never come back. Or if I look at it in terms of Y, I come in for a fixed value of Y, stay, and then leave. So this would be an example of an X simple region, a Y simple region, or a simple region. Can somebody give me an example of a region that's not simple? If you have trouble I'm sorry? If you have trouble, think of Homer Simpson and feed him. Donuts. Donuts, right? If I give you a donut, or a really bad donut, it is neither x simple nor y simple because I come in, I stay in the region, I leave the region, then I come back to the region, and then I leave the region. So this is not simple. It turns out integration over simple. But what we can do is we can split this like the following. And if we split it like this and call this region 1 and this region 2, it's the union of two simple regions. And so what we can often do is we can break a general integral into two simpler integrals. All right, so this is a good place to stop. And then, oops. And then the next class will be